All right.
Let's talk about something we use every single second of every day, but can't actually see: electricity. The best way to think about it? It's a language. And by the end of this, you're going to be fluent in the basics. So let's dive right in.
So think about it. You flip a switch and boom, light. You plug in your phone and it just starts charging. But how? Seriously, how does that invisible energy travel from some power plant, maybe hundreds of miles away, through all those wires and into our homes with such perfect precision? Well, to get that, we have to start with the absolute basics, the path it has to take. And that path is everything. It's the #1 non-negotiable rule of electricity. It's called an electric circuit. Just think of it as a mandatory round-trip journey. For electricity to do anything useful, it needs a complete, unbroken path to travel, from the simplest little flashlight to a massive supercomputer. If that loop isn't closed, nothing happens. It's really that simple.
Okay, so to really get a grip on this, we're going to start at square one. We'll begin with the most basic form of electricity out there. It's called direct current, or as you've probably heard, DC. This is that nice, straightforward, one-way street of power, kind of like what you get from a battery.
You know, no matter how crazy and complicated a circuit might look, it really just boils down to two main players. On one side, you've got your sources. These are the things that generate the energy, like a battery. And on the other side, you have the loads. They're the ones that consume or use that energy, like a light bulb. Connect a source to a load, and boom, you've got a circuit.
All right, now for the vocabulary lesson. There are 3 words you absolutely have to know to speak circuit. First one up is voltage. The absolute best way to picture voltage is to think about water pressure in a hose. It's the potential, right? The push that's all ready to make the electricity start moving. The higher the voltage, the stronger that push is.
Okay, so if voltage is the pressure in that hose, then current is the actual flow of water through it. It's the measure of how much electricity is actually moving through that circuit at any given moment. So remember, voltage is the potential to flow, but current is the action.
And that brings us to our third and final key term, resistance. Let's go back to our water hose analogy. Resistance is like pinching the hose in the middle. It's an obstacle, a kind of friction that restricts and slows down that flow of water. In a real circuit, every single component, even the wire itself, has some resistance. It's what pushes back against the current. So there you have it. Voltage, current, and resistance, the essential building blocks.
Now, DC is fantastic. It's simple, it's predictable, perfect for batteries and small electronics. But it has one massive problem. It's terrible at traveling over long distances. You just lose way too much energy. And that was a huge roadblock for building, well, the entire modern world.
This became the central question for the early pioneers of electricity. I mean, how on earth do you get a gigantic amount of power from a hydroelectric dam way out in the mountains, send it across hundreds of miles of country, get it to a city, and then into your house, without it all just fizzling out? DC just couldn't do the job. They needed a completely new way of thinking.
And the solution they came up with? Oh, it was an absolute game changer. It literally changed the world. It was called alternating current, or AC. And this is the type of electricity that comes out of the sockets in your wall right now.
So unlike DC's simple one-way street, AC electricity flows one way, then flips and flows the other way, back and forth really, really fast. Now you might be asking, why is that so revolutionary? What's the big deal? Well, it's because this oscillating nature makes it incredibly easy to step up the voltage to super high levels for long-distance travel with minimal loss, and then step it down to safe levels for use in our homes. It's absolutely brilliant. But because AC's flow is constantly changing, that simple idea of resistance we talked about earlier, it's not quite enough anymore. It doesn't tell the whole story. So we need a new, beefier term, impedance. You can just think of it as the total opposition to the current in an AC circuit. It's kind of like resistance's more comprehensive bigger brother.
So, we've got our amazing AC power grid, but here's where things get really fascinating. There's a catch. It turns out that not all the power that's flowing through the grid is actually doing useful work. To be truly efficient, we have to understand the different types of power that are at play.
And this is a really interesting question to ask. You might assume that all the power a factory or a big building draws from the grid is being used to run machines or light up rooms. But the answer, surprisingly, is no. There's this hidden, unproductive part of the power that's essential, but it doesn't actually do any real work.
Let's break down these 3 faces of power. First, you have active power. This is the good stuff, the hero of the story.
This is the power that performs real, useful work, like turning a motor. Then you've got reactive power. Think of this as a necessary sidekick. It's essential for creating the magnetic fields that motors need to operate, but it doesn't do any physical work itself. And finally, there's apparent power, which is just the grand total, the combination of both the useful and the reactive parts. It's what the utility company actually has to supply.
So the key metric here is the ratio of useful power to total power, and this is called the power factor. Ideally, you want a power factor of 1, which means 100% of the power is doing useful work. But a poor power factor, like this 0.70 you see here, well, that means only 70% of the power being supplied is actually useful. The other 30% is just reactive power, basically sloshing back and forth in the wires doing nothing productive.
And a bad power factor has very real-world consequences. It means the utility has to supply more total current just to get the same amount of useful work done. This leads to things like overloaded transformers, dangerously hot wires, a ton of wasted energy, and, you guessed it, much higher electricity bills for industrial users.
But luckily, there's a really elegant solution to this. Instead of drawing all that unproductive reactive power from way back at the power plant, large facilities can install banks of what are called capacitors. These things act like little local reservoirs of reactive power, supplying exactly what the motors need right on site. This improves the power factor, boosts overall efficiency, and saves a whole lot of money.
Okay, let's move on to our final big concept and see how this all builds up. The power that comes to your house is called single-phase AC. It's fine for your TV and your toaster, but for the really big stuff, we're talking giant industrial motors, huge data centers, and heavy machinery, that's just not going to cut it. They need a much bigger, smoother, and more efficient delivery system.
And that system is three-phase power. For large-scale applications, it's simply better in every single way. It's more economical to transmit, it lets machinery be more powerful for its size, and most importantly, it delivers power in a constant, smooth stream, which is exactly what large motors need to run efficiently without vibrating themselves to pieces.
So what is it exactly? Well, a three-phase system is basically three separate AC signals, all perfectly synchronized, but just slightly offset from one another by 120 degrees. Imagine three pistons firing in perfect sequence in an engine. This setup ensures that as one phase is dipping in power, another one is already rising to take its place. The result? A continuous, unwavering, smooth delivery of energy. So there you have it. Look how far we've come. We've gone from the simplest little battery and a light bulb all the way to the sophisticated systems that power our entire industrial world. We've learned the basic vocabulary of electricity.
And if you look back, our journey shows this really clear pattern of innovation. We started with the simple one-way flow of DC, but to go long distance, we needed that massive leap to the AC revolution. To make AC truly efficient, we learned how to tweak it by managing the power factor. And to power our biggest machines, we scaled it all up to three-phase. Each step was a brilliant solution built right on top of the last one.
You know, understanding this language isn't just about the past, it's about the future. From smart grids and renewable energy to electric vehicles and the next generation of computing, all of it is built on these fundamental principles. So the real question is, now that we can speak this language a little better, what new conversations are we going to start, and what incredible future are we all going to build?